All right, so our objective on these problems is to draw the shear force and bending moment diagrams. We'll start with the one here on the left first. Again, I'll save you a little time and I'll tell you that the shear on this side is P over 2. And the shear on this side is minus P over 2, right? Because a force acting up is that positive shear or negative shear? That's negative. So that means we should start at P over 2 and we should end at negative P over 2. Now, what are our differential relationships? Well, the first one is that the change in shear is the area under the load curve. So let's start here and look at just the distance L over 2. What's the load there? That's zero load. So that means we should have no change in shear. So if I start off at P over 2 and I have no change, what should I get? Should stay at P over 2. And our differential relationship says that the shear, the slope of the shear, is equal to the load. And what's the load over this first length? 0. So that means the slope should be 0. So we get a constant shear over the first part of the beam. Now, as we move from the left side to the right side and we pass underneath this load, what happens to our shear? Remember, we had that additional thing that we knew, that the change in shear is directly equal to the load, right? What kind of load is that? Is that a positive or negative load? Negative. So I should go from positive P over 2, I should instantly subtract P, and that should get me to negative P over 2. Now the change in shear between these 2 points is given by this expression, which is the integral of the load. And if you look up here, the load is 0. So the area is 0, and it matches. There's no change in our shear. The slope of the shear diagram is equal to the load. What is the load? 0. So 0 slope, horizontal line. And there is your shear diagram. What's the maximum shear in the beam? P over 2. Okay, let's do our moment diagram. What do we know about the moment? Do we know the moment anywhere in the structure? At this reaction, the moment is 0. And at the roller, the moment is 0. Now our relationships tell us that the change in moment is the area under the shear diagram. So what's the change in moment from 0 to L over 2? It should be the area under the shear diagram, which is P over 2 times L over 2, which is PL over 4. So I should get a value, a positive value of PL over 4. The slope of that curve is equal to the value of the shear. What's the value of the shear everywhere here? Well, first of all, it's positive, and it has a value of P over 2. So here's my positive slope, and if I actually marked it off, it would have a slope of P over 2 to 1. Now the change in moment between L over 2 and L is the area of the shear diagram from L over 2 to L. And what is that area? Negative P over 2 times L over 2. That's negative PL over 4. So positive PL over 4, Minus PL over 4 brings us to 0. Great, it matches. The slope is what? Equal to the shear. And what's the value of the shear? Negative shear, so negative slope. And it's constant. And if you were to track that, you would see this be minus P over 2. And there is your moment diagram. So what's the maximum moment in the structure?
PL over 4.
PL over 4. Where does it occur? At L over 2. Okay? Let's try the next one. So this one has an intensity of W. Remember, that's force per length. So again, if you look at the reactions, what you should get here is WL over 2 for the shear on the left side, and WL over 2 for the shear on the right side. This is positive shear force. This is negative shear. So that means I'm going to start at a positive shear of WL over 2, and I probably should end at a negative value of WL over 2. So hopefully this will match. So the change in shear is the area under the load curve. Well, my load is continuous the whole length L. So what's the area under this load curve? It's a rectangle, base times height, so it's WL. Is that positive area or negative area? It's acting down, so it's negative. So I've got positive WL over 2 minus WL gives me negative WL over 2. So that matches great. So that part's checked. What's the slope of the curve? What's equal to the load? And the load is constant. And it's positive or negative? Negative. So we get a negative slope. So if I were to check the slope here, it would be negative W0. Now, when your shear passes from a positive zone to a negative area, you need to really identify this crossover point. And how do we do that? I've drawn it here because I kind of knew before it was happening, and I'm saying it's happening in L over 2. But how do you know it really happens at L over 2? Well, you may not. But you can use your relationship to figure it out. If I project that point up to the curve, what would be the change in shear from here to this point? Let's say I don't know this. Let's say it's some value x. So what's the change in shear from here to here? How much is the shear changing? It starts at WL over 2 and ends at 0. So how much does it change? Negative WL over 2, right? So I know how much it changes. At the same time, what's the area under my load diagram? So I project this up. What's this area right here? For an arbitrary distance x. It would be Wx, and it would be negative. These two things are equal, right? So I should be able to solve for x. And when you solve for x, you get L over 2. So you can use the same rationale to find any place when the shear crosses over. Now, why do I care about where the shear is 0? Well, look over here. If the shear is 0, that means the slope of the moment diagram is 0. What does it mean to have 0 slope? That usually indicates that your curve is peaking up and dropping down, or going to a minimum. So that's going to probably indicate a maximum or a minimum for us. All right, so let's finish this and draw the moment diagram. So I have a shear diagram. I'm pretty happy with that. What's my moment at the left edge? at this pin? You guys can play along. No one knows? This is pretty sad if you don't know the moment at a pin. Thank you.
Oh, goodness.
What's the moment at this pin? Oh, now you're with me. So, the change in moments, the area of the shear diagram. What's the area of this part of the shear diagram? It's a triangle. 1/2 base times height. Now remember, this is not x. What is it? It's L over 2. So I get WL squared over 8. Half, 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 right? So that means that I should get positive WL squared over 8. What's the shape of my curve? Well, the slope of my moment diagram is equal to the shear. What's the value of the shear right here? It's positive. So I'm going to draw a big positive slope. It decreases to a slope of 0. Here's a 0 slope. What kind of curve fits that? Now, I know I'm at WL squared over 8 positive. I want to find out what happens from L over 2 to L. So change in moment is area of the shear diagram. What's the area of my shear diagram here? Negative W squared over 8. So positive minus that brings me back to 0. Yay. Now the slope of my curve is equal to the shear. So the shear starts off with a value of 0 slope, and decreases to a fairly large negative value. Negative value. So this was a positive slope. This is a negative slope. And if I try to fit that in there, it probably doesn't look like it, but that's a nice parabolic section. What's the maximum moment? WL squared over 8. And where does it occur? Right in the middle. So any questions about that? We'll just keep this up as we move forward. So